Welcome back. In the previous video on climate change and mitigation, it was discussed that we need our energy infrastructure, that heavily depends on fossil fuels and CO2 emissions, to be turned into an energy system based on renewable energy technologies. In such energy transition, renewable electricity, like solar electricity, will become the dominant energy carrier. In this video, I will discuss the role of solar energy in the energy transition. The learning objectives of this video are to understand that the transition that the energy system has to undergo along the energy value chain from generation, transport, storage, and consumption. You will be introduced to energy transition models towards 100% renewable energy future and in infrastructure, and the typical timescales to introduce and integrate new technologies in an energy system. Finally, you will understand the role of solar energy in this energy transition. Our current energy infrastructure, as simplified in this visual, depends on energy carriers as oil and oil products like gas and coal. They are consumed in the various sectors like transport, industry, households, agriculture, and public services. Coal and gas are used in plants to convert this chemical energy in either electricity or heat to be used in the above sectors. This infrastructure is demand-driven. When industry or household needs more electricity, the plants will operate at higher capacity, or in other words, burning more coal or gas. The electricity is centrally and transported in one direction to industry and households. The storage functionality is within the primary fossil energy sources. These are directly consumed in the sectors like gas and coal in industry, oil products in transport, or converted into electricity and heat to be consumed in the various sectors. Consumption of energy in this system leads to CO2 emissions. The next visual shows a future energy infrastructure in which fossil fuels are replaced by renewable electricity. Wind and solar energy is directly converted into electricity using wind turbines and photovoltaic modules. The electricity supplies all energy needs for households. In certain regions in the world, gas-powered residential heating will be replaced by electrical power heat pumps. Fossil-based combustion engine in transport will be replaced by electromotors. In this system, the dominant energy carrier is electricity. This system is not demand-driven anymore, but supply-driven. The energy generation depends on when the wind is blowing and the sun is shining. In such energy systems, storage of energy becomes an important factor as well to guarantee the reliability of the energy supply. Electricity generation has been decentralized. Many wind parks, solar parks, and photovoltaic systems integrated are installed on many locations onshore and offshore. Transport of electricity becomes more complex. The electricity grid has to facilitate bidirectional transport as well. A detailed model entitled Global Energy Systems based on 100% renewable energy was published by the Energy Watch Group and Christian Breyer of the LUT University in Finland. This model simulates global energy transition for all regions in the world in detail from 2015 towards a 100% renewable energy system in 2050. This model does not need carbon capture in the second half of this century to meet the targets of the Paris Climate Agreement. This is in great contrast to the IPCC CO2 emission scenarios towards 1.5 degrees Celsius and 2 degrees Celsius temperature increase at the end of the century, discussed in the previous video. The primary energy sources are heavily dominated by the fossil fuels like oil, coal, and gas, with a minor contribution of nuclear and biomass energy. The model uses existing renewable technologies like photovoltaics, wind turbines, batteries, heat pumps, and electrolyzers. By replacing this energy infrastructure, the model shows that to realize a 100% renewable energy system, the role of wind and solar electricity has to grow significantly. To 18% for the energy in the form of renewable electricity is supplied by wind and 69% by solar energy. A minor complementary role is for biomass, hydroelectricity, and geothermal energy. The model simulates this transition in steps of 5 years. This graph shows the primary energy demand per capita and how it's distributed over the energy carriers like electricity in green, heat in red, bioenergy fuel yellow, and fossil fuels in light orange. It demonstrates how in time electricity will become the dominant energy carrier and will replace fossil fuels. In 2050, 90% of the energy supplied is electricity. What are the costs of such energy transition? This graph shows that the levelized cost of energy can stay under 60 euros per megawatt hour or 60 euro cents per kilowatt hour. The cost price consists of capex, opex, fixed, opex variable, grid costs, fuel cost, and CO2 cost. Capex stands for capital expense and covers fixed assets such as buildings, equipment, and land. OPEX stands for operating expenses and is the ongoing cost for running a business of system. Here distinction can be made. OPEX fixed are the running costs regardless of how much business is made, where OPEX variable are running costs that change with the amount of business. The figure shows that by the introduction of renewable technologies, fuel and CO2 costs are phased out, while capex of the renewable technologies is increasing. It is an inspiring model that demonstrates that with existing technologies, a transition towards a 100% global renewable energy system is technological feasible at no additional costs. The model shows that on the generation side, the capacity of installed wind and solar electricity generation has to drastically increase. Is such quick growth possible? Can such supply chains from materials, manufacturing and installation of photovoltaic systems be realized? In this graph, I show the evolution of the effective power delivered by different electricity generation technologies. After the invention of the Francis turbines in the late 19th century, the first hydroelectricity dams were constructed and taken in operation. Note that the vertical axis is on a logarithmic scale. The hydroelectricity power has grown exponentially up to the 60s of the last century. Nuclear electrical power has been introduced in the 50s, as shows an exponential growth up to the mid-18th of the last century, and the installed power capacity then quickly saturated. Saturation means that just as much operational capacity is installed as is being dismantled. Every system has a technical or operational lifetime, after which it needs to be replaced. Also plotted are the increasing capacity of solar and wind electrical power. Both technologies are still in an exponential phase. You can simply divide the evolution of installed capacity for a technology in 3 phases. The last phase is the replacement market. Just as much capacity is installed as is dismantled. The annual installations are determined by the total installed operational capacity divided by the lifetime of such system. The first phase is that both total installed capacity and annual added new installations is exponentially growing in time. The first phase ends at the point when the annual installed capacity does not grow anymore. The supply chain of materials, manufacturing, components, and installation and its annual market can never exceed the replacement market in the last phase to guarantee a financially sustainable supply chain. I understand that this is complex, but it basically means that the maximum sustainable installation market, the transit from phase 1 to phase 2, is reached at a time span before the start of the replacement market in phase 3. This is equal to the lifetime of a system. What does that mean? Let's take the projected global needed wind and solar power capacity following the earlier introduced global energy system based on 100% renewable energy in 2050 as an example. Wind supplies 18% and solar 69% of the electricity supply. This means solar and wind capacity needs to maintain an exponential growth of its annual market up to 2030 to establish the required annual market needed for the next 25 years after 2030 to realize a 69% share in the total mix of power capacity. It means that in 8 years, an annual market of 3 terawatts should be realized. Next to the model of the Energy Watch Group on global energy system based on 100% renewable energy, I have introduced in this video. Many other models have been published in scientific literature by scientists, associations, governmental advisory committees, and the industry. Do all these models result in the same final topology of the future energy system? The answer is no. I demonstrated that with the next graph out of a paper I have co-authored together with many experts around the world. The metric we use here is the penetration of solar and wind energy to the energy system. With other words, what is the final share of solar and wind energy to the total energy mix? The penetration of solar is plotted on the horizontal axis and the penetration of wind energy is plotted on the vertical axis. As you clearly can see, the results of all models scatter broadly in the wind-solar penetration space. Why do all these models give so many different results? Many reasons can be given. The quality of the technical models that simulates the operation of the energy system. What is the time relation? To what detail and space are the components in the energy system worked out in the model? Another aspect is the assumptions put in the model and the quality of the data used. As you can see here, the integrated assessment models of the 5th assessment cycle of the IPCC resulted in a rather low penetration depth of solar energy. The reason being, outdated cost data for photovoltaics was used in these models. Cost prices for 2050 were assumed that were higher than the cost prices already realized in 2020. It's logic you will arrive at a lower solar electricity penetration. In the 6th assessment cycle of the IPCC reports, a lot of progress has been made in understanding the role of solar energy and its costs. In the IPCC's report on mitigation of climate change 2022, this bar graph was published. The graph shows the potential contribution to net reductions in CO2 emissions by 2030 per technology. The length of the bar shows the amount of net reduced CO2 emissions expressed in equivalent CO2 emissions per year. The colors along the bars represent the cost per additional reduction in net emission. The blue color represents that corresponding technology is cheaper than the reference based on a CO2 emitting fuel. The graph basically shows that wind and solar energy are the technologies that on short term can have the biggest contributions to replacing CO2 emitting energy technologies with renewable electricity. In addition, these technologies are for large parts, see the blue color, cheaper than the fossil-based technologies. In summary, the maturity and the cost price for solar energy predicts a dominant role of this technology in the future energy mix. In the next video, I will discuss how photovoltaics can contribute to improving the access to electricity to everyone in the world. See you in the next video.